Okay, so we're on section 10.4. The book calls this inscribed angles, polygons. I'm not sure I would call it that. I would call it inscribed angles and 3 corollaries. You have any idea what a corollary is? A corollary is another truth, at least in math anyway, it's another truth that falls easily on the heels of a major big truth. So we're going to have a big major theorem called inscribed angles. It's very easy. And then there will be 3 other conclusions we can draw from that. So here we go. First of all, you need to know what an inscribed angle is. Can you all see clear over here and see this picture, even though it's a little bit flattened? Yeah, you okay with it? Okay. What we said before this class was that if you have a central angle, the central angle A, I'll put an O here. The central angle AOB, whatever its measure is, that's the measure of the arc from A to B in degrees. They're both measured in degrees, right?
Yep.
You follow me? Okay. If I were to take this, like if these 2 green pieces were green rubber bands, and I grabbed it right off the center here like this and pulled it backwards until I dropped it right there, then I would have this angle right here, the black one, and it is called an inscribed angle. This was a central angle. This is an inscribed angle. What it means is that the corner is on the circle and the angle itself opens out into the circle, hitting a piece of the circle as it opens out. Inscribed circle has its vertex on the circle. Now, how do the sizes of them compare? Well, that's why I've got this thingy here. I'm going to measure that green one. And keep in mind, every single thing on this picture has been free-handed. Didn't measure or use a straight edge or a compass on anything. So don't expect this to come out perfect, but it'll come out almost completely convincing. Okay, what I'm going to show you. So if I put this on here, put this on one side, and even though that green line wasn't very straight, if I go from here up to D right there, this angle right here appears to be just slightly short of 120. It's obtuse. I'm going to say it is 120 and give myself a little leeway because it was free-handed. Okay?
Yep.
Okay. Now, look at the size of the angle that we made by pulling that back on a rubber band. So we put that right on the C and stretch that up towards B. And this one comes across right there, and you can see right there that that's 60. So it appears that what happened is, whatever this angle was before we pulled its vertex back to sit on the circle, this was 120, this was 60. They appear to be in a ratio of 2 to 1, which is exactly what it is. That's the theorem that's the inscribed angle theorem. And so what we're saying is that if I take this central angle out, because that's not the subject of today's lesson, I just wanted to show you how it's related to what we studied before. If I take this angle out right here, then since that central angle I just erased and this arc have the same measure, we can say that an inscribed angle is half the measure of the intercepted arc. That's exactly what the inscribed angle theorem says. Inscribed angles equal half the intercepted arc. And you got to know what the intercepted arc is. It's the arc that is formed when the angle goes out far enough to hit the circle twice. That arc that is in, if I were to continue this on out like this, it's a little easier to see if I do that. If I continue these on out like this, then it is the arc that is inside the angle, that piece of circle. Okay? And if that measures 120, then this measures 60. And if this measures 60, this measures 120. 2 to 1. Everybody good?
Yep.
Okay. So that's the first major theorem, and it wasn't very hard to understand. It wasn't very hard for your mind to grab onto either. Now, the next one, the reason I've drawn this in color like this is because I want you to focus for a second on the green angle. And the green angle, APB, if I extend those out like I did before, then it's pretty easy to see. And I don't want you to actually draw these lines in your book. I want you to use your mind to imagine it. The intercepted arc here is arc AB. And so whatever the measure of arc AB is, P is half of it. But I want you to also notice, and this is really easy to get once you've seen it all explained. This is easy stuff. If I extend the red angle, called angle Q, and if I extend that out on the edge right there, you can see that its intercepted arc is also AB. Without knowing anything about the measure of arc AB or P or Q, I can definitely determine this. Whatever arc AB is, whatever all of these numbers are, this angle has to equal this one. Because they're inscribed on the same arc. So they're half the same thing. So they have to be the same thing. That's pretty easy, right?
Okay. Oh, sorry. I didn't quite grasp that.
Can you see the green angle as it comes out right here? Arc AB is the one that's inside it.
Yes.
Do you see that if I extend the sides of the red arc as it comes out here, arc AB is the arc inside it?
Yes.
You do see that? Yes. If they intercept the same arc, then they have to be the same size.
Got
it. Okay. All right. Two angles that intercept the same arc are equal. That's a corollary because it was based on the idea that an inscribed angle, when it hits the arc, is half the size of it. But if they both hit the same arc, then they're both half the same thing. So that's called a corollary. The main theorem is this, that an inscribed angle is half of its arc. This is a corollary that leads right off of it. If you intercept the same arc with two different angles, those angles have to be the same size. Does that make good sense? Mm-hmm. Ready for the next one? Yeah. So we're okay there, right? Yeah. Okay. On this one, if I draw a triangle in a circle such that one of the sides is a diameter, we know that it goes through the center. I mean, that's something you can have just observed. If I extend this out like I've been doing all day, if I extend that out here and this out here like that, then the arc intercepted by angle, inscribed angle B that's out here on the circle, the arc that's intercepted by it is 180 degrees. Yeah? Makes this 90 every time, which is kind of cool. If I erase this and these extensions here, what I'm saying is that you can, as long as one of the sides is a diameter, I could draw a triangle like this. That would also have to be a right angle. This one would have to be a right angle. Has to be, because every single one of these, like these over here, are inscribed on the same arc, which is 180 degrees. Do you remember what we called half of a circle? Remember we called that it was a stupid name, but it kind of said what it was supposed to. Instead of saying it's a semicircle, we called it a semi-arc, meaning a semicircular arc. Just shortcut, we called it semi-arc. So the way we're going to phrase this is an angle inscribed on a semi-arc is right. Does that summarize what we've just been talking about? Is that okay? Do you follow all that? Yeah. Okay. All of these have to be the same because of this corollary, and they all have to be right because of what we just discussed about the diameter there. They're all inscribed on the same arc, so they're equal to each other like this was. Everybody good so far? Yeah. Okay, this last one, this last of the three corollaries can be a little rough to get. So I'm going to go slow. And just like you did, I want you to tell me if you get lost or you don't see what I'm saying. Because this is a little bit hard to get. For some of you, you get it right like that. And you go, what's so hard about that? But others of you won't see it immediately. Please let me know, and I will say it slower and louder. Maybe you'll get it. All right. So I want you to look very carefully at this. This, by the way, this weird shape, including the blue and the red, if you go all the way around, that's a quadrilateral because it's got four sides, right? Not only that, it's called an inscribed quadrilateral because all four of its corners are on a circle and it's inside, inscribed inside. This quadrilateral is inside and we call it inscribed. It wouldn't be inscribed if we had something like this. You could have a quadrilateral inside a circle, and some of the vertexes can be on there and some of them maybe not. That's not an inscribed quadrilateral. An inscribed quadrilateral has to have all four of its corners as points on the circle. But as you can see, it doesn't seem to matter what the shape of the quadrilateral is. Just so long as all four of its corners are on the circle, then this will be true. So can you all see that the blue angle, ABC, that's an inscribed angle because it's got its corner on the circle, right? Okay. Can you see that this is its arc of inscription?
Yes.
Everybody see that? So it's arc ADC. It's probably a major arc. Well, it is a major arc because this is greater than 90. So arc ADC is the arc that this inscribed angle is inscribed on. Yeah?
Yeah.
Take a look at the red angle right here that comes out like this. That one's acute this time. The angle, or sorry, the arc that it is inscribed on, and go out to the edge of the angle right here, and we come around here to the other angle that came around right there, stops right there. And so arc AC is what D is inscribed on. Okay, now here comes the part where you got to reason. Can you all see that the blue arc and the red arc make up the entire circle?
Yeah.
So they're the entire 360 degrees, which means that this angle, blue one, and this angle, red one, has to add up to 180. Because they're half the size of their arcs, and their arcs add up to 360. Does that make sense to you?
Yeah.
Yeah.
Anybody not understand so far?
So we're trying to find the angle, not the arc.
Arcs and angles, it doesn't matter. What I'm trying to say is that if you look at the blue arc, which is what the blue angle is inscribed on, and the red arc is the red arc over here that it's inscribed on, the blue and the red arc all the way around make up the entire 360 degrees. And these blue and red angles are exactly half of those arcs, whatever they are. And so these must add up to 180.
Yeah.
Do you remember what we call two angles that add up to 180? Supplementary. So this is how we are going to summarize this corollary, as long as everybody's with me so far. You hanging in there with me? Okay, so this is how we're going to summarize this. An inscribed quadrilateral of any shape. Could be a rectangle, could be a rhombus, could be just about it. Well, it could be a rhombus. No, could be a rectangle or a square. Could be this ugly thing here. Has to be convex. All the corners have to point out because that's the only way they can connect with the circle right here. But an inscribed in. An inscribed quadrilateral has supplementary opposite angles. So it was pretty clear. Well, after I hope you all understood. It's the blue and the red one are supplementary. But I could have made the exact same argument for this angle coming out and taking this one up, and this angle coming out this way and taking that up. These two are also supplementary. Opposite, if it's an inscribed quadrilateral, then opposite pairs of angles, either one, either this pair or this pair, they have to be supplementary. So that if you know how big angle A is, you can find angle C by simply subtracting it from 180. Do you all agree?
Yeah.
Okay, same thing for D. If you know what D is, you can find B. Now, if you know what D is and that's all, you can't find A and C, but you could find B. You following?
Yes.
Okay, so this is the main thing, and these are the three corollaries. This is the theorem. This is corollary 1. This is corollary 2, and this is corollary 3. The main theorem says that an angle is half of its intercepted arc if it's inscribed. So with all of those in mind, the example should go pretty quick. I want to show you just so you can see a quick application. It's not very hard. You ready?
Mhm.
Okay. Example 1 says, find the indicated measures. What's the measure of angle T?
24.
Measure of angle T is 24. Good. What's the measure of arc QR? Careful. Anybody? B. Here's why. Because arc TQ has to be 100. Do we agree?
Yeah.
Yeah.
And arc TQR has to be 180. Do we agree?
Yes.
Yes.
Because of the diameter on it. See it?
Okay.
So the 180 minus the 100 we got from the inscribed angle gives us that QR is. So there's a little bit more to do on that one, but it all came from that theorem. Do y'all follow?
Yes.
So remember, things that look like diameters are diameters, and it makes a 180 on either side of it as an arc. And that can help you make some calculations. Okay, look at example 2. Look at the situation they've got there. We got a 31 in angle U. The question asks, find the measure of RS. 62. What's the measure of RUS? RUS.
62.
No, RS is 62. How big is RUS?
31.
Not angle. Arc, RUS. I'm asking the questions here, not the book, not the book. I'm asking the questions.
So that's like,
62?
okay, that's like 200.
298. Because the entire thing is 360 and RUS is what's left over after we determined that RS was 62. Now, how big is angle RUS? Oh, brother, that's what I marked. Wait a minute. That's not what I wanted to do. How big is angle STR? Angle. Angle. Make sure you know what you're talking about, whether there's an arc or an angle. How big is angle STR? 31. Because they're both inscribed on SR, right?
Yeah.
Okay, moving on. Look at example 3. No, I don't want to do that because we already did one just like it. Okay. Turn over to page, or example 4 on page 556. Example 4 says, find the value of each variable. What do you think? What's the value of x, just x, in 4a?
45.
45, because angle C has to be 90. So x has to be 45. Does this make sense?
Yeah.
Okay. Look at angle, look at B part right there. How big does Z have to be?
80.
Try again.
100.
100. They've got to add up to 180. They're supplementary. They're not equal, they're supplementary. How big is what is Y?
60.
60. Y'all see it?
Yeah.
Did I lose anybody?
No.
Okay. There's an interesting little thing, though no, I don't think anybody would ever do this, but there's an interesting little thing over there on example 5. Just look at it for a minute. We're looking at a bird's eye view of the Statue of Liberty, and she sits on that great big huge square platform. See it? We're looking down on it.
Yeah.
And the question asks, where could you stand so that your camera, which has a 90-degree aperture opening, where could you stand and get a full shot of that statue, the front of it? And the answer is anywhere on that circle in the second picture. Because anywhere on that circle, when you face the statue, is going to give you a full shot 90-degree angle of it because of this. Okay?
Yep.
That's it. Inscribed angles and 3 corollaries. Here's the assignment. Ready? This is section 10.4, and it is 3 through 21 odd, 25 to 30, and 33 and 35. 3 through 21 odd, 25 to 30, 33, and 35. That's 18 questions. It's a little more than a couple of days, or the last couple of days, but still, it won't kill you. So there you go.
33 to 35.
33 and 35 on the end.